All right. Today let's look at how to do a blast analysis inside LS-Dyna with a card called low blast enhanced. Basically, it's going to look like something like this. This is a quick example I put together, and I'll talk about this at the end. Okay. All right. So overview of blast analysis. Agenda today basically is we're going to look at the basic theory and setup behind this card. Excuse me. And we're gonna look at, also how the physics behind blast wave actually work, because when we do blast analysis, we have to sort of understand the physics behind what we're trying to model. And then we'll look at a few examples, like a basic plate with a cell and shell, with a solid and a shell. We'll look at a basic plate example with an obstacle, and then we'll look at like a cage, for example, as well when we look at it together. Okay, and then lastly, we'll look at how he handles obstacles, basically, is the second example. Okay, so the basic theory behind low blast enhance. So let's look at the card first, right? So the low blast enhance is basically just this little card right here that is going to ask you to find XYZ location of your source of your blast wave. This M parameter here defines the weight of your TNT material that's going to be under explosion. So this thing is actually based on an analytical result, also based on experimental results that we're going to talk about in a second. And then there are about four different blast wave, blast law, blast parameters that we'll look at only the one of them, which is an open air blast. That's a sort of a spherical blast wave. And there's a couple other ones that we could be looking at as well. Okay, and then the low blast enhanced card, the blast enhanced card is going to require a low blast segment card, which is going to basically define the way the elements or the segments where the blast wave pressure load is gonna essentially be applied to, and we'll talk a little bit about what that means in a second. Okay, so this is the basic overview. So this is the sort of the keyword template. For each segments that we're treating as target, we're gonna need a specific low blast enhanced card. So the BID is a number of different kind of blast wave sources that we have. For each segment set, we're gonna have essentially one source we're gonna be applying that to. Is in essence what's happening. Okay. All right. Let's look at the basic sort of physics behind a blast analysis. I'm learning this as I go as well. Certainly not something that I've done before, but it's pretty interesting just to learn a little bit about it. And then you sort of draw the correlation between the physics itself and the way the LS-Dyna implement the model to represent that physics, right? Which is the whole idea behind here. Okay, so let's say for example you have a source, which is the source of your blast wave, your blast pressure wave, right? So when you define a source, you're defining basically how much explosive you're using, what the location is, and what kind of profile is that blast wave. So in this case, when we use a blast of 2, we basically have a spherical um, pressure wave that's going to be applied, right? So when the wave starts, you have what's called an incident wave. That's essentially the red, which is going to travel until it hits the target. When it hits the target, a portion of that is going to transmit across the target, and another portion of it, usually a big portion of it, is going to basically bounce back. It's going to get reflected back, and that reflection plus the incident shock wave together defines the applied pressure that's actually applied at the segment level, which is essentially like on the element itself. Okay, and that's really the basic logic of a low blast enhanced, is that we're not actually applying a wave that's traveling across a medium. What we're doing is to apply that nodal pressure or the segment-based pressure, which then turns into a nodal force. And that's what happens when you see something that looks like this happens. Is that what we're actually doing here, right? Something like this is that we're actually just applying that force on the node itself. Of course, that follows a profile, which we'll talk about in a second, right? So the low blast enhanced, the basic theory essentially is the Friedlander pressure function, or the Friedlander equation. Basically, it follows a pressure wave that looks like a pressure function that looks like this, right? So you from here to here, you have sort of the travel time. So at this point in time, the pressure the low start, the pressure starts, and it's gonna follow a triangular curve. This overpressure right here basically is a combination of both your incident and your reflective pressure wave, right? And then once you hit the peak pressure wave, it's gonna sort of goes to a positive phase where you have this area under the curve, which generate a positive pressure. and then after a certain amount of time, after the R plus right here, it's going to go into a negative phase, which the pressure becomes negative. And that's because the way the air is being compressed. So that sort of has that retraction that happens. And this is a really interesting type of physics to visualize. But basically, people who studied this many decades ago came up with this type of function. There are resources I will share in a second. Okay, so this law right here basically governs the nature of the pressure wave that's being generated inside a blast analysis. So for example, if I were to look at, in this case, I have a two plate which has a pressure wave source, right? So yeah, if I were to play this, actually maybe I should just play it this way, right? So you see, so basically this right here, that initial little pressure wave right there, right? You see how this curve basically follows the Friedlander equation that it's generated here, right? Because what we're essentially doing here is with this. Now you can actually get rid of the negative phase as well if you wanted to, but that's the basic physics of what's happening. Now what we're doing here is that we're applying this pressure load curve onto each segment inside on the target itself. Okay. Now, the way the pressure is applied is actually we're not just applying the same thing over every single segment, right? So, for example, if this is this is a snapshot I took from one of the guideline documents from LSTC, but basically, if you have a source of the blast, right, and your segment is over here, you have the angle of incidence, which actually is what ultimately defines the effective pressure, which is the pressure that includes both the reference pressure and incident pressure. Okay, so that's the key things here to remember is that depending on the angle between the normal of your segment and the radius of from the center of the segment to the source, that changes how the pressure is applied, which is why you see a gradient on the plate down here. So if I show this plate right here, you can sort of see this is a gradient right here, and then my scale is set in such a way it's not so clean, right? So I could make something like this, so you can sort of see the target is right in the center, and then you can see when the angle of incidence is close to sort of 0°, then you get a really perfect pressure, and then otherwise it gets sort of dilute down as you go outward and outward and outward, where the angle gets smaller and smaller and smaller. Okay. All right. So this is the basic logic for how the pressure is applied. Now the obviously the pressure is a function of distance, right? So when we know the pressure is a function of distance, but it's actually not calculated directly inside LS-Dyna. I think it's used it actually uses how I'll show that real quick in the reference right here. 1 second. So there is a document that was created many decades ago. This is the 1997 paper, which sort of implemented the air blast flow model inside LS-Dyna, the Dyna 3D right here. So this document right here basically provided the resource for defining how the pressure is applied based on the experimental results that was done on a different type of explosive. So you feel free to read through this. I haven't read through all of this yet, but basically, given the nature of the test that was done, that is implemented into the code. So when we define a low blast enhanced, this is predictive engineering. But when we sort of model the low blast enhanced, the actual pressure value comes from that study, which is implemented in the code, right? There's a ConWeb app that's also or not app itself is not integrated, but the data came from the same location, which is how we know what amount of pressure is actually being applied. Now the low blast enhanced has a scaled range value, which is which is based on the amount of mass you have on the TNT plus the radius, which is from the center of the segment to the source. Now this number, the model is only valid when the number is between these two values. Depends on the nature of what kind of blast model you're using. So in our case, we're using number 2, right? Where the Z value needs to be between 0.147 or 40, which means that it can't be too far away. You also can't be too close. That's essentially what it means, right? So the more you use, the further away you can go. So there is a range of essentially what this essentially measure is of all the segments that's within some range of the source. The blast model is only accurate when it's trying to map pressure over. Otherwise, it's not really accurate. So this is just a quick math we have to do every single time we do a low blast analysis to make sure that the Z value is between the range depending on what kind of blast model you're using. This is very important, obviously, to pay attention to. Now, the effective impulse is one of the things I wrote down in my notes in the slides. because this is the one of the most important thing I can imagine that being as an indication for how much energy you are putting onto your structure through the blast analysis, right? So by looking at your pressure wave, you can look at the you can integrate that over time to see exactly how much energy you're putting into the system. And that's a great way to compare different kind of blast load and to see if your structure is under risk or not. Okay, so when there is a obstacle between your target and the source load, basically the pressure map that's mapped, there's a shadow region which is no longer going to be accurate. So to demonstrate that, what I did here was I have a source, so I can show the model real quick before I do that. Actually, let me show the model real quick. So if you look at this model right here, the blast source is happening inside here, right? You can't exactly see that, can you? How can you see that? That's weird. But basically, the blast center is right in the center, right? That's basically where we have the blast source. And then I have a low blast enhanced card that's being generated here. And then the segment that I'm applying to is a segment down here for the shell. And I have a segment down there for the solid. And I have two fixed support on the edges of the plate. And then I'm just applying a low blast enhance across those two segments, which is gonna do 20 kilograms of TNT, and it's gonna apply a pressure wheel onto these two plates. Right now, the question here is that what happens if you have two smaller discs, which is blocking the view of the center point where you have the blast source, right? And when that's the question, you know. So what I did was I could look at the pressure gradient for the sample where you don't have any blockages. You can sort of see in here, you have the equal pressure gradient across each side right around that time in the pressure wave. But when you do have the obstacle in place, right, the plates no longer sees that same load because you treated the smaller disc as a target as well. Now, if you don't treat the smaller disc as a target, which means in the blast file you're not going to be able to see anything. You get effectively the same response as the top side, and in this case, this thing is not really blocking the pressure wave, right? So the shadowing is only becoming a problem when you have one target that's in front of another target. So when you are studying about blast analysis, I think so. I wrote this down to remind myself that if I have a more complex geometry, I need to pay attention to the view, to basically it's like a view factor in a radiation analysis. I have to figure out the view direction of my surfaces of my segments, so I don't have sort of like shadowing situation going on. This is where the pressure mapping is no longer accurate. Okay. All right. So but when you do have an obstacle, right? One of the biggest thing with this type of analysis is that the reflective pressure wave is actually way higher than the incident pressure wave. But what we're mapping with the Friedlander equation is the combination of both. But in reality, what happens is that the pressure will bounce back and forth until it reaches equilibrium, right? So what I sort of wrote down here is to understand that the reflective wave is usually like 2 to 13 times bigger than the incident wave. And this is the actual physics, right? Is that we're actually going back and forth. So there's a story where I read that in the quick research I did, is that if you're a person in front of a blast and then behind you is a structure like a building, you're actually under a much higher risk and a much higher damage because the pressure will bounce back and forth between the building and yourself, and you're actually gonna take a lot more damage that way because the reflective pressure wave is so much higher. So to keep that in mind, right, with the low blast enhanced, it's a much simpler model where what we're doing is that we're defining a source, then we're applying pressure on the target. That's all we're doing. There's no reflection happening. But in a future video, I'm going to do more investigation with the ALE method to do this type of analysis where we are able to see the pressure wave transfers. And that's the type of thing I'm very interested in learning how to do as well. Okay. All right. So so I basically have these two models. They're very simple models that I've generated, right? Nothing to it. What I also like to do at the end of this video is to look at an example that look like this. So I'm going to do this one. This is what I showed in the beginning of the analysis. Right, in this case, what I have is I have a source that's happening right there, right? Then I'm applying a high amount of explosive load, and then just blow away this cage. I just want to set it up to show with a structure that's slightly more complicated. We can also leverage the segment pressure wave tool inside LS prep post to check essentially where of all the segments that I selected are being seen by the source. So it's a very good way to check how is your pressure load going to be applied before you run an analysis. Okay, so let's do this at the end. I have a model prepared. I'll hide these two. And I have a dummy model that's right here that I'm ready to show. Okay. All right, so this basically is just like a cage. There's nothing to it, right? You see there, I have a disk right there. I prepared the cat to use that disk as the source of my explosion. So I'm gonna select this surface and I'm gonna select there. You see now I have a origin right there that is going to be I'm gonna change that to global coordinate system. So this is basically 2 meter. I'm changing this to MKS. Okay. This is 2 meter. Oh, that reminds me, it's very worthwhile to mention. In the low blast enhanced, you see the units parameter right here. I didn't talk about it. This units parameter defines the unit system these cars are under, right? So to 2 means MKS, meter kilogram second. But if you use other units, you have to change this parameter right here. So in this case, everything is going to be MKS, and my analysis setting is going to be set to MKS as well. I'm going to make sure I do that before I forget. Okay. All right, so I now have a global coordinate system here. So I have a 200 coordinate, which I'm going to use in a second. And now I can basically suppress this because I no longer need that body. Now for everything else, I have a steel material assigned. So within this steel material, what I did was I have a basic mat 003 with a mat elastic plus a bilinear isotropic hardening that's defined here, right? 450 megapascal for yield and then some tangent modulus. What I also have down here is a mat eye erosion where I define 5% tensile strain and 15% equivalent strain as the failure criteria, which means I define this steel to fail at 5% total tensile strain and 50% total strain. Okay, so that's essentially what we're doing for representing the erosion for this material, right? So if I show you real quick, right? So if I use, so it's basically just this is right here. This parameter right here is I think it's MXEPS, and this one is ME. Oh, let me double check my card. I don't remember my card. Erosion. Right, so basically it's MXEPS for tension, and then EFF for the total effective strain, and that's what we're doing here for the mat eye erosion. Okay, in terms of meshing, I'm gonna make this super simple. I'm just gonna do 0.020, 0.040, and then I think because the way I did this was I have everything as the swivel body, like that, so I don't have to worry about it. Let me double check my original setup to make sure I didn't miss anything. Oh yeah, I guess I should do a sweep. Oh, I don't have anything name selection created, so let's just do this. Let's put there. That's all of the body, and then what I'm gonna do here is that I'm going to deselect this one and this one. So the first sweep has only 3 element corner thickness for each of all of these body, and for the other one, what I'm gonna do for the other one is I'm just gonna make them into a sweep, but I'm not gonna define cross sections, so you can mesh properly with the right amount of elements. And then the mesh here, I'm gonna use 40 millimeter, and I'm just gonna mesh it. This just create a minimum amount of element required for this type of analysis. And then what I'm also going to do is, okay, right there. What I'm also going to do is to take advantage of the auto contact detection method inside the workbench measure to basically do all body. And then I'm gonna do like 0.001, and then I'm gonna do actually 0.00. That's 1 millimeter, and then I'm gonna just auto select. And what this should do is I should select all of the possible contact pairs in this model. Yeah, should. And then what I wanted to do here is these are all basically contact mesh, and I'm just gonna do, yeah, this is fine. And then the only thing that I want is I want this one to have a tie break contact, because I want a top thing to basically blow open, which is what I have in my original model. So what I'm gonna do here is I'm gonna insert a tie break contact from my keyword template. And you see I have this space here empty. What that's gonna do is that's gonna take these two surfaces and put that into this card. And there I have 100 megapascal as sort of like the contact pressure required to debond this top board. So if you look at what I have in the video down here, is that I actually have that top layer separating from the rest of the cage. You see there, you see that contact separation that happened right there? That's because I have that tie break contact on the top. I just want to check against that. Just some extra little spice I'm adding to the model. Nothing really that important. Okay. Now from here, what we have to do from here is to basically create a bunch of surfaces that's going to represent all of the inside surfaces of this. So what I want to do right now is select all of the inside surfaces of this thing. Okay, so what I can do here is let's go to selection and select all faces. Oh, actually, I'm do this. Select all faces, and then I'm going to right click, name selection, and call this the inside segment blast. Okay, I'm gonna call this 9996, and then I'm going to also select these, add it, select this one, add it, let's select these, add it, and let's select these, add it, select top face, add it, and I'm gonna hide the top face so I can look at it better in the inside. What I also wanted to do here is to make sure I select this face and add it. Okay, I think that should be all the inside face, right? I believe. Maybe I can select here as well. Yeah, I should select the other face as well. Select these faces. Okay. Now what I've done here is, if you look at what I've done, is I have now selected all the inside faces inside this box, because all of these faces are the potential target for the blast wave. Okay. Now remember, my blast source is located where I created the coordinate system, which is at 200. So, and I'm gonna set the termination time to something like 0.001 or something like that. This is a really short duration. I don't have to run the analysis for too long. Maybe a little bit longer. 0.01. Okay. Let's fix the bottom surface. Fix the floor. The whole thing stays. I have my contact already selected, right? So everything's bonded together. And now I'm gonna generate here is I'm gonna generate a low blast enhanced card. So this is something that, if you are following me along, make sure you do it yourself, right? Instead of just, I'm just copy pasting from what I've already done. What I've did here is just walk through it. This thing's located at 200, which is the 200 coordinate right here. So it's located right there where the blast source is going to be. I have a blast 2 type at unit 2, which is MKS. Blast 2 is a spherical free air blast. And then I'm applying to the segment 9998. So I need to change this setting to 9998. Okay, and that's what basically what this pressure is I need to change this back to 1. Okay. And then that's basically what it is. So with this, that's my low blast wave, right? And then what I need to do next is I need to basically just add some basic database cards. So one interesting thing I didn't mention in the slides is that for the blast analysis, you definitely want this database binary blast 4. All right, what this is going to give you is basically all the actual plot that we're looking at here is going to come from the blast analysis. Obviously, this is not exact. This is the effect plastic strain, but if you want to look at the pressure wave, right, like I'm seeing here with these curves, you need to have the blast 4 being implemented, which I will show you in a second. Okay. All right, so with this, that's pretty much everything we need to do, right? We have our fixed support. If I want to be strip, I can change the section assignment for all of these bodies to be a fully integrated SR solid, which is if I want to be strict. And of course, I should go ahead and disable my database cards and disable my control cards. And now I can write this out. I'm just gonna do low blast demo. Okay, and let's call this the demo card. All right, and I'm gonna open a new session for Alice Prepos. I have a bunch of them open already, right? I can sort of show you what happens in here is that because this one is already solved. So if I go to binary plot, and then if I were to open that model right here. You see this blast floor right here. If I want to open this, what this will gives you, what this will give me is, so just loading. All right. Anyway, so while that one is loading, let's go ahead and load in our new demo file. Because what I want to show you is a way to check your blast segments. There's some error in the model. I'm demoing this. Maybe I missed something. Let's double check. It looks fine. Okay. Anyway, so what we can do here is if you go to application, you go to segment pressure wave, right? In here, I can set check the radial, and then I can select my position to be 2, 0, 0. Speed doesn't. I'm gonna do like 10, whatever, and then it's gonna be radial. Decay is gonna be something like that. That's fine. I can pick my target element. And in this case, right, instead of selecting everything that's inside, like I did before, what I can do is I'm just gonna select all of it. And I right-click my mouse to return this menu, and then I click Apply. And what this is gonna do is I'm gonna calculate all of the segments where from the perspective of the source of the blast, what can you see, what can you not see, right? So it's invisible nodes 32256 elements that much, invisible nodes that much. So all of the invisible nodes will be happening on the outside. And it's something that you can sort of double check. Obviously, I was being lazy when I selected everything on the outside. You can select more carefully to see if certain segments can be seen by the blast source. So this tool right here is very useful to look at for this kind of analysis. Okay, I'll cancel that. And then if you look at here, what we can also do here is that we can actually look at the pressure, and then I can sort of get like if I want to just run real quick, you can see boom, and you see where you see all the pressure changes. That's high pressure. These scales are not very good, so what I can maybe do is get the scale to be a little bit better. So do like 1e to the 5e to the 7, maybe better, right? So if I just play this, boom, boom, that look pretty cool. Let's do 1e to the 7. Maybe I get a little bit better pressure wave look that way. Yeah, you can see that pressure wave travel across it. Isn't that pretty awesome to see that? All right, and that will be the end of the video. Thank you very much. I'm hoping this is helpful. All right, bye-bye.